Hi everyone, today's topic is about Word2Vector. It is a method to represent the natural language in vector space so that the computers can find the similar words by understanding the context of words. Well, let's kick off to see how we can do it. There are two methods for implementing Word2Vector. The first method is cbout and the second method is skipgram. The cbout method tries to predict the central word given neighboring words, and the skipgram method predicts the neighboring words given a central word. Let's say that there's a sentence, today I received a gift from my friend and it made me happy. And let's say that the central word is received, then the neighboring words will be today I a gift. And in the case of cbout, we are trying to predict the central word received given the neighboring words today I a gift. And in the case of skipgram, we are trying to find the neighboring words today I a gift given the central word received. However, in real implementation, the stop words are removed from the sentence, and the stop words refer to the words that do not really affect the semantics of a sentence. So let's look at how to prepare the training data. In the corpus, there are two sentences, and firstly, you need to extract unique words from the corpus, and they are sorted in ascending order, and each word is indexed starting from 0 to distinguish each unique word, and they are called vocabulary. And if you look at the table, the first column gives a list of words that belong to the corpus, and the second column is the vector representation of the words, and the third column is the output labels for the corresponding input data on the first column. So let's take two examples. In the case of today, the vector representation, it is denoted 1 at position 7, but 0 for all other positions. And it is because if you look at the vocabulary, the index of the word today is at index 7. So to represent the word today in vector space, you denote the position 7 as 1, but 0 for all the rest of positions. And today being the central word, the neighboring words will be received and gift. And let's look at the index of the word received in the vocabulary. It is at position 6. So you denote the training label position 6 as 1. And also, if you look at the gift is at index 1. So you encode position 1 as 1. So the output labels are encoded as denoting position 1 as 1 and 6 1, but all other positions 0. Now let's look at the second example, friend. So if you look at friend, the word friend in the first sentence, this time it has neighboring words on the left. So you denote all positions that belong to received, gift, made happy in the vocabulary as 1 in the vector representation. So let's see the index of received. Received is at index 6. So the output label, the position 6 is denoted as 1, and gift is at index 1. So index 1 is denoted as 1, and then the word made is at index 5. So if you look at index 5, it is denoted as 1. And then if you look at happy, it's at index 3. So index 3 is denoted as 1. So all these 4 positions are denoted as 1, but 0 for all the rest of the positions. In the earlier example, the output labels were compact in one vector space. However, this time we want to store them individually. If you look at the first row, the central word is today, and the neighboring words are received and gift. And these are the 100 encoded representation of two words respectively. And the second input data is received, and the corresponding neighbor words are today, gift, friend, and what we are trying to implement is skillgram. And remember that skillgram is trying to predict the neighboring words given the central word. So the first column represents the central word, and the second column represents the neighboring words. So for the first row, third row, the word is gift, and the 100 encoded representation is, as you see here, O1, O, 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 O. And the reason dimension is 9 is because the total vocabulary size is 9. And what we are trying to do is that we want to predict the neighboring words of gift, which are today, received, friend, and made. And all the rest of the rows are encoded like this. Along with the training data, we have to prepare two wave vectors. The first wave vector represents the vector space for the vocabulary, and we'll be updating them during the backpropagation process to represent the condition, the distribution for the training data, which is based on the skillgram model. And the second wave vector is used to conduct the inner product of the hidden layer to get the output layer, and we'll be going to see it soon. The training process is based on Feedforward network. The hidden layer is created by taking the inner product of the target word and the first wave vector. And the shape of target vector is 9 because the size of the vocabulary is 9. And as you saw earlier, the first wave vector is in the shape of 9 by 10. And if you take inner product of these two matrices, it ends up with a hidden layer with a shape 10. Once you got the hidden layer, you can calculate the output layer by taking the inner product of the hidden layer and the second wave vector. The shape of the hidden layer is 10, and the shape of the second wave vector is 10 by 9. And if you take the inner product, it gives the output layer of shape 9. And next, you pass the output layer to the Softmax function, and it will return probabilities for each element. And if you look at the expression of the Softmax function, the argument is the ith element of the vector z, which is the output layer in this case, and the Softmax value of the ith element of z is the exponential of the element over the sum of all the elements taking the exponential. Now you can calculate the error rates with the prediction probabilities. Here's the prediction probabilities we just got earlier, and we subtract the vectors of all the context words of the corresponding target word, and you get 3 rows of error rates for the corresponding context words. And for example, in this sentence, today I received a gift from my friend and it made me happy. Let's say the target word is received, then the context words for this target word is today, gift, friend, and the corresponding vectors are on this column, and you subtract these vectors from prediction values. And then if you list all these error rates, you sum them up all by row wide, and you get the final error rates. And once you got the error rate, you take the outer product with the hidden layer and the error rate and store it in delta W2, and it is called backpropagation because you are going backwards to take the derivative of the error rate. And if you look at the diagram, the hidden layer is of shape 10 and the error rate is of shape 9, 1, and if you take the outer product, it will return a matrix of 10 by 9. And second, you take the inner product of the second wave vector with the transpose of the error rate, and the diagram you can see below, W2 is 10 by 9, and it is the matrix we had initialized with the uniform distribution at the beginning, and taking the inner product of the transpose of error rate, which is of shape 9, 1, will return a matrix of shape 10, 1. And lastly, you calculate delta W1 by taking the outer product of the target word and the matrix we just calculated. And for example, let's say we have a vector gift for the target word, and if you take the outer product with the W2 inner product transpose of E, then which is of shape 10, 1, then it will return a matrix of shape 9, 10. Once you got the wave vectors for delta W and delta W2, you can update the initial weights of the vectors W1 and W2 with the learning rate. The learning rate lets you determine how much step you can take towards updating the weight vectors. The larger value means that you take larger step towards changing the weight vectors, and the small value means that you take small step towards changing the weight vectors. And you repeat these steps so far until the loss is minimized. The overall process is that you take a feedforward network in which you created one hidden layer, and then you go through the backpropagation process by passing the error rate to update the weights of the vectors. And the loss function is can be calculated as follows. It consists of two parts. First part is to sum up of all the elements in output layer for the context words, and then the second part is to multiply the length of all the context words, taking the log of all the sums of the output layer, taking the exponential, and then you take the negative of value A and add B to it, and it can be the loss of the value. Finally, we are given with the output vector W1, which are the updated weights of the initial vector that we had initialized with the uniform distribution. To get the vector of the corresponding word, for example, friend, you get the index of the word friend, which is 0, and you find the vector at index 0 of the weight vector W1. So if you want to get the vector of the word happy, then you get the index of the word happy in vocabulary, which is 3, and you return the vector of W1 at index 3, which will give minus 0.07, 0.51, 0.97, 0.57, 0.76, 0.27, 0.54, 0.92, 0.05, 0.86. So with this vector space, if you want to find similar words, you can calculate cosine similarity of two vectors. For example, if you take cosine similarity of happy and joyful, it will give a probability like 0.56. In addition to finding similar words, you can also find the context of a word. Say, if you want to find a similar word of small in the same sense that the word big is similar to biggest, then you can do it with simple algebraic operations like vector biggest minus vector big plus vector small return of vector smallest on well-trained Word2Vector. So to wrap up, if you want to find the similar word of happy, then you take cosine similarity of each pair in the vocabulary and you sort them in descending order, and the word that has the highest cosine similarity will be the similar word of happy. In this case, joyful will be the similar word of happy. And for a detailed explanation of cosine similarity, you can refer to the link I'm going to put in the description box below the video. I am planning to make one in the future, and also the code of Word2Vector I have implemented by myself is available in my GitHub, and I'll put the link also in the description box below the video. So up to this point, I have covered about Word2Vector and talked about how the computers can understand the context and find synonyms and similar words. So I hope you enjoyed it, and thanks for listening. Bye.